Hi, this presentation is going to consider counting principles within the context of probability. We can start this discussion by looking at the fundamental counting principle, which states if any one event can occur in m ways and a second event can occur in n ways, the number of ways the two events can occur in sequence is m times n, right? So the product of those two things. And this rule can be extended for any number of events occurring in a sequence. So it doesn't have to be just M and N. It can be any letter of the alphabet ad infinitum. So here's an example. We have a meal consisting of a main dish, we have a side dish, and we have a dessert. How many different meals can we put together if there are 4 main dishes? In terms of options, 2 side dishes or 5 desserts. And it's simply a multiplication of those options. So we have the 4 main dishes, the 2 side dishes, the 5 desserts. Multiply those together, you get 40. So there are 40 possible meal combinations. Here's another example of flipping coins. And if you flip a coin, you have a 50-50 chance of getting a head or a tail. So if you flip 2 coins, you can look at this graphically in this way. We have the first coin. Let's say we're going to flip it twice, so we get heads the first time. Then maybe we get heads or tails the second time. And then the other coin we flip and we get tails, and maybe we get heads or tails the second time. So there are 2 ways at both steps where we can see the event unfolding. So we just multiply those together. We get 4. And we can apply the fundamental counting principle to calculating the odds of somebody cracking the code on a home's security system. Let's say you've got a 5-digit code, and each digit can range from 0 to 9, which is pretty typical of a keypad. And if we're going to calculate how many different codes there are possible, we need to answer this question first. Can we use the digits more than once? And if each digit can only be used once and not repeated is the other option. So in the first case, because each digit can be repeated, then there are 10 choices for each of the 5 digits. And that's simply going to be a product, 10 times 10, 5 times, right? So we have 100,000 codes. Because each digit cannot be repeated in the second scenario, there are 10 choices for the first digit, 9 for the second, 8 for the third, and so on. So you can see a factorial coming in there, right? 10, 9, 8, 7, 6 for those 5 separate events, which gives us 30,240 codes. So significantly fewer potential combinations if we can't repeat the code. So if you are designing a home security system, make sure people can repeat the code. So in that previous example, we saw a permutation, which is an ordered arrangement of objects. So the number of different permutations of n distinct objects is n factorial. And you can recall which of the examples had this characteristic, and that was the second characteristic here, where we see this factorial design come in. So n factorial is n times n minus 1 times n minus 2 times n minus 3 ad infinitum. So for an example, how many different surveys are required to cover all possible question arrangements? If there are 7 questions in a survey, that's 7 factorial, and that gives us 5,040 different surveys. Another thing we can introduce to this notion of permutations is taking n number of objects, r at a time, which is expressed mathematically in this way. Number in the group is n, r is number taken from the group. So if you're dipping your hand into a bowl of jelly beans and you're pulling out 10, how many of those are going to be red, for instance? That would be a good application of this formula. And the math of that is simply n factorial over n minus r factorial. So if you're going to take 5 books from a list of 8, and we want to know how many different orders you can do that, we simply express that as 8p5. So 8 factorial over 8 minus 5 factorial, which is going to be 8 factorial over 3 factorial. These cancel each other out. 3 times 2 times 1 over 3 times 2 times 1. That just, anything over itself is 1. That's why those cancel out. That leaves us with this portion of the numerator over 1, which will be 8 times 7 times 6 times 5 times 4, giving us 6,700 720 different ways to select 5 books from a list of 8. Which maybe that's surprising. That's a large number. Next, we can talk about distinguishable permutations. And the number of distinguishable permutations of n objects, whatever those are, whether they're roses or poker chips or cards in a deck, where n1 are of one type and n2 are of another, and so forth, is expressed with this equation, which is n factorial over n1 factorial times n2 factorial ad infinitum, where n1 plus n2 plus n3 plus ad infinitum equals n. So for an example, we have Jessie who wants to plant 10 plants along her sidewalk in the front yard. She has 3 roses, bushes rather, 4 daffodils and 3 lilies. And we want to know how many distinguishable ways the plants can be arranged. So first we start with the number of plants, which goes in the numerator, which is 10. That's n. Right? That's a total number. So 10 factorial goes in the numerator. And then down in the denominator we have these 3 separate types of plants, the rose bushes, which are 3, the daffodils, which are 4, and the lilies, which are 3. And so we wind up with 10 factorial over 3 for 3 factorial. That gives us 4,200 different ways to arrange the plants. Next we can look at combinations, and combinations are different from permutations because the order does not matter. When we have a security code with 5 numbers in a row, the order of those numbers matters, so that's a permutation. If we had a security code where the order didn't matter, we could just type the same 5 numbers but in any order we wished, well then we'd have a combination. And so what we're looking here is a combination of n objects taken r at a time, and that's expressed here. And the C is indicative of the combination rather than the permutation. So the number in the collection is n, and the number taken is r. Here is the formula. We have the total n on top, factorial, divided by n minus r factorial times r factorial. And that's the part that distinguishes this from the permutation equation that we saw before. So if you're required to read 5 books from a list of 8, right, and how many different ways can you do so if the order doesn't matter? Now it's just simply 8 factorial, which is the total list, divided by 3 factorial times 5 factorial. So the math of that comes down to simply 56 combinations, which is far less, you'll recall, than if we back up and look at the permutation example. Sorry, here you go. We saw that if the order mattered, there'd be 6,720 different permutations. But if the order doesn't matter, there's simply 56 combinations of books. Here's one more example applying the counting principles that we've been reviewing. Let's say there's a state lottery where you have to select 6 numbers out of a total possible 44 numbers to win the grand prize. And it can be in any order, so that means we're talking about a combination, not a permutation. That would be rather astronomical if the order mattered. And some lotteries, in fact, the order does matter. But here we've got, we can lay this out in terms of the way we've been talking about combinations. We have 6 numbers chosen from 44 numbers. If you choose one lottery ticket, what is the probability of winning the top prize? There's the 44 there, 44 possible numbers, and the 6 that we're taking from that. So we take the factorial of 44 and divide it by 6 factorial times 38 factorial. Right? Add those together, you get 54. And there we get the math. 1 over 7059052. There's a lot of zeros. Not a very good chance of winning the lottery. We have 1, 2, 3, 4, 5, 6 zeros. Not a very good chance that you're going to be winning the lottery because there are 7,059,052 combinations.